capital P, so it became lowercase p, which is now nice to differentiate the academic version with what is in the product. What we did after acquisition was to start a Europe R&D center in Munich, where we now have a little over 30 full-time employees. And then we have parts of the HyPer team in Seattle and Palo Alto. And in early 2018, we were done with our first integration into the products. What we replaced, and we'll talk about, was the Tableau data engine. And we've shipped in all on-prem and SaaS products at the time. In mid-2018, what followed was Tableau Prep. That's Tableau's data preparation tool that also uses HyPer as its processing engine. In mid-2019, we released HyPer API, which exposes the full HyPer SQL capabilities to Tableau partners and customers. And the focus of this year was to develop further as a general purpose database service in the Tableau platform. Few words about Tableau, if you don't know it. It's BI and analytics platform, mostly known for its data exploration capabilities and visualization side, but there is a lot happening in the background, from natural language processing to statistical exploration, to data processing, to data preparation. So why on earth did we start building a database system in 2008? There were many factors. Two we want to talk about here. One was the obvious debate that's always going on. Does one size fit all use cases? And I think the answer there is definitely no, right? There will always be a vast majority of database systems out there. But what you usually find today is transactional systems, the systems of record that are being deployed. You find data warehouses for analytics, and you find beyond relational stores, graphs, key value stores, specialized systems for data mining, Hadoop clusters, NoSQL systems, and so on. And so, yeah, it's obvious, one size does not fit all. But the two things that we were interested in is, one, there is a data lag between a system of record and your analytics, right? You do have ETL in the middle. It takes a while for the replica to catch up. And so you have this inherent data lag. And the other is you have a lot of data by now that is fairly disconnected from the relational world, right? So how can you analyze all these things together? The second context under which we've been operating and starting a new database was a vastly changing hardware landscape. Just showing two trends here that happen and continue to happen. One is memory prices falling over time. In recent years, we've seen that flatten out, but for many years, the drop was near exponential. And so a gigabyte in 1996 would have costed you a fortune. Today, it's very cheap. The other trend on the CPU side is that, yes, Moore's law is still holding. You have an increasing number of transistors, but it's not as easy anymore to really leverage these transistors one-to-one for performance. So CPUs have become very complex, a lot of cores, very deep pipelines, larger caches. And so in order to leverage modern hardware, both memory and CPU, it was very evident that you need to design a database from scratch to really make best use of the hardware resources you have. And so this was the second context we've been starting building a database system under. And the idea behind HyPer is to combine operational processing, so data ingestion, transactions, streaming, with analytics capabilities on the latest state of the data. And then in ideal world, we could also bring in beyond relational capabilities, so we can also query relational data together with non-relational data. And of course, because we were in academia, we could go wild. We said, okay, we want to optimize for all underlying hardware, from phones up to the cloud. The three operating systems we, of course, did not do from the get-go. We started out on Linux. and Mac was a smaller step, although not trivial, right? But then when we joined Tableau, it was also a necessity to run on Windows. And so having the three in the mix, and we'll hear about that when we speak about testing and quality, that can be a challenge, right? Now, the design principles we've been operating under and continue to do so at Tableau is that we want to build one system, as said, for transaction processing, ingestion, analytics, that operates on one state, so we can really have real-time analytics on a fresh state of your data. We made no trade-offs when it comes to asset guarantees and SQL language support. Our SQL interface is based on the Postgres dialect with fairly large extension set, and we also speak the Postgres protocol. And then, of course, databases are always about performance, right? So we want to have no delays. We want to scale with the available hardware resources that are given to us to really allow for highest performance in all workload classes. Inside HyPer, the things largely published. You can find that at hyperdb.com. That's the academic website that lists all the publications from our academic past. And so we've always optimized for the storage hierarchy, bringing data as close to registers as possible. Fundamentally, we are based on query compilation. We have a vectorized scan subsystem that's underneath the compiling engine. We have invested a lot in logical query optimization, have fast MVCC under the hood, and have the Morsel-driven parallelism to really make best use of the cores we're having on a specific machine. In Tableau, HyPer is, you can think of as a database that ships with the products or is deployed with the products. Tableau has fundamentally many modes how it can connect to data, one of which we call live mode. So in that mode, you connect Tableau to your SQL Server database, to your Oracle database, to you name it. We have many partners, many connectors. And what Tableau would do in this mode is you do your exploration, you build your dashboards, you do your data preparation, and send SQL queries to these engines, gets the results back. The second mode we have is and sorry, my cat is screaming, of course, during the keynote. And the second mode we have is what we call extracts, where you can extract out part of the data into HyPer, where the query processing then happens. And so those are the two modes we have, and some in between where HyPer plays the role of an accelerator. Now, the fundamental thing is the interface to Tableau is based on SQL and giving back results, and that powers a wide range of Tableau products. So yes, where were the challenges going from HyPer with capital P to lower P? We can only talk about a few. There have been many more along the way. It's definitely been a fun time. The biggest ones were certainly around support. Tableau products are on-prem and in the cloud. The on-prem versions do have a fairly long support cycle. That is a challenge for any software product. Comparing the performance across releases, and especially if you switch out database engines, is really challenging. We'll hear about that. There are semantic differences, of course, when you do this, and those also become very difficult. Infrastructure, as said, we run on Windows, Linux, and Mac OS. That's really as hard as it can get, probably. Small laptops to large-scale servers and cloud deployments. And then in the workload, we see a long tail of very complex queries generated by Tableau and wide variety of dataset characteristics. And with that, I want to hand over to Jan, who will talk about the specifics and what we did to ensure great quality for our customers and test on a continuous basis.
All right. Thanks, Toby. Next slide, please.
Yes.
So let's start with talking about Tableau workloads. So we already published this in the last DBTest workshop where we had a paper about this. So the gist is most queries in that Tableau generates, right? So these are all generated queries. They are not written by a human. So most of them are small. So only 0.5% are larger than 5 kilobyte SQL text. But think about it, 5 kilobytes is already pretty large for a human to write. But of course, for a machine to generate, it's nothing, right? We have huge outliers. For example, in our data set where we test with, it's like 6 megabytes of SQL text. That's a book full of SQL text just for a single query. And we've also seen a query like with 27 megabytes of query text. That's half a bookshelf full of query text for a single query. And that's not all due to constant strings, right? So it's not like that there's one string which is 5 megabytes. No, it's a real query. You see here one of our smaller query trees, and you see that's already comparably big if you compare it to a TPCH query tree, for example. Next slide, please. Here we have it a bit with more details. So you see it already looks pretty big, but it's a small query, and you see the dashed lines going from left to right. So it's already been shrunken down by our query deduplication mechanism. So wherever you see a dashed line, it deduplicated a query tree. So if you didn't have that deduplication, this tree would already be like 10x larger, right? And as a side note here, if you want to visualize your SQL queries or your relational algebra like that, we published this as an open source query graph viewer. So you can just download it on GitHub and play around if you want to visualize. Next slide. Here's just to show you the magnitude of what we are talking about. These are the biggest queries we had in our public data set by the number of operators. And you see the largest query has around 1,000 operators, 270 table scans, 230-ish group bys, 250 sorts, 160 inner joins, and so on. So you see really a lot of operators in a single query. If you want to know more about that, check out our paper from DBTest 18. You find all the statistics in there. Next slide. So you see, like, it's a pretty hard workload, right? And that workload before was running on Tableau's old data engine. So now how do we replace that with HyPer? The old data engine was called TDE, so just Tableau Data Engine. It was a vector-based engine inspired by MonadDB X100. And so our first step was, well, we have to replace it as the backend of all Tableau products. And of course, the goal was to deliver performance at scale, right? We don't want to slow down. We don't want to be slower than the old engine, right? Of course, the best would be to be faster than the old engine. And we want to have a seamless transition for customers. So it may not be that, oh, the products now ship with HyPer and everything just fails, everything crashes. That may not happen, right? To the customer, it must look like as nothing ever happened. Maybe things get faster, but there may not be any other ways to see that we switched out the engine. Next slide. So the cool thing about changing an engine, replacing an old engine, was that the old engine was somehow the gold standard. And having such a gold standard is an absolutely great thing to have, right? Because what you just do is, we just ran a lot of workbooks from Tableau Public. For those of you who don't know, Tableau Public is our free offering. But what comes with this free thing? The free thing is that your workbook is open source basically to anyone, right? So we, from a perspective, from a legal perspective, we were allowed to just take the workbooks from there and run tests on them, compare the results, see whether HyPer has the same result as the old engine, see how fast HyPer is. So it was a good, simple and measurable goal. We just have to make sure that all the results match and we're fast, and then we're done, right? So it's pretty cool. In the beginning, it was like, oh my God, half of the results are different. Then it's like 10% of the results and so on. And we knew, like, okay, once all results are the same and we're fast, we're done. That's pretty cool. That's a very measurable goal. Next slide. But for example, there were some challenges with that. For the first one is bug compatibility. yeah, do you want to copy all the bugs from the old implementation? That's the question. And or on a more general question, is it really worth to show always the same results for all queries? It might not even be a bug, it might just be non-deterministic behavior. For example, the old engine didn't parallelize a lot. HyPer parallelized way more aggressively. So it could be that you get different results just because of the non-deterministic nature of parallelization. But it could have also been bugs, and there were some bugs in the old engine. And it's a very interesting thing how our attitude with these bugs changed over time. In the beginning, it was absolutely like, okay, we have to be the same at all costs, right? No visualization may change. Customers want to see the same result. This is non-negotiable. If anything changes, we cannot ship HyPer like that. But then we were like, well, but what if the visualization was wrong before and now it's right? Wouldn't we like the customer to see rather correct results? And then we were like, okay, who said that? Who said that it's non-negotiable? Who said that visualizations can't change in the first place, especially if they change to be more correct? And then in the end, we ended up and said like, okay, it's okay if visualizations change if they were wrong before. Let's do the right things. Let's not copy bugs, because we now have the historic chance to get rid of the bugs. Let's do it now, because if we don't do it now, then we can never, ever do it again. So that's a good learning, right? If you can, don't copy bugs. I want to show you, here's one example of such a, well, I wouldn't even call it bug, but it's a behavior that we didn't like. And it's about casting strings to date. In SQL, you can cast strings to date by giving a pattern, or you can cast them to date without giving a pattern. And this is for without giving a pattern. If you just have the string 5/7/2020, is that April 7 or is that July 5, right? It depends on the order. Is month first or is day first? So TDE, what did they do? Well, they tried to be very aggressive in finding a valid date. Give the user some value at all costs. That sounds good, right? But it's horrible in the relational model, because in the relational model, you don't have a single value. You have a column of values. And if you see in this example, if you have a column, either the month is first or the day is first. It will probably not be the case that in the first row, the day is first, and in the second row, the month is first. But this could happen with TDE. For example, in this example, 5/7 would be April 7, but 15/7 would be July 15. So that's pretty weird. In HyPer, we say like, nah, rather let's pick one date style and display a null value instead, right? Because with the null value, the customer sees, okay, there's something wrong. If they just receive valid dates, they don't see something's wrong. And there were silent failures with that. For example, you had a sales workbook and you wanted, why do I have more sales in the first 12 days of each month? Is it that people buy more in the first 12 days? No, you just parsed your date incorrectly, right? So, yeah, so that's something where we say like, no, we don't want to reproduce that. And we had many more of those stories, but we're time constrained. So we have to stick with this one. Next slide, please.
And Jan, if 5/7 should never be April 7, would probably be May.
Oh, yeah, sorry. Yeah, you're right, Toby. May 7, sorry. Also about performance, right? We tried to outpace TDE, but of course, as I said, it was an engine based on MonadDB X100. So it's a good engine, right? And it was read optimized. TDE was a read-only engine. So they could play all the tricks that you can only do in a read-only optimized engine. In HyPer, we want to allow hybrid processing. So we don't want to optimize for read-only. So we tried to be as fast as possible, but of course there were some workbooks. Maybe we were fast in 99% of all cases, but there were some workbooks where the old engine was still faster. But you see that over time, we still invested into performance. It was not that after the HyPer launch, we said like, okay, we're done. We've got it shipped. So we just leave it where it is. But in the following releases, so you see here in this graph, you see the releases 10.4.11 is the last release with TDE, and the releases afterwards are with HyPer. And you see here, it's 10 different queries. And you see in some of them, in the first release after TDE, we were way slower. Oh, so that's not improvement. Sorry, that's how much slower we were. So if we were at 3, it means we were 3 times slower than TDE. But you see over the releases, we invested heavily into performance, and some of them got way faster than TDE. So that's also something to take home, continue in investing into performance, right? Even though HyPer was fast, HyPer had data blocks, HyPer had model-driven parallelism, HyPer had query code generation, all that, there's still a lot of room to optimize further. Next slide. So now this is DBTest. Let's get to how do we do testing with HyPer, right? Because in a next slide, please. In an industry setting, you have to test harder than in academia, right? For your benchmark, it's okay if just the benchmark works, but with other inputs, it's ZAG faults. That's of course not okay for a real product, right? So we had to have a lot of test coverage to be sure that our quality is good. Of course, the first thing is SQL level testing. You want to test something, here's a SQL query, what should the result be? We started as many with the SQLite test suite. It's available, it's open source, it's a huge body of tests. So we started with that. You can see an example in the upper right corner. It just goes like, here's a query, then here's a query that select date or something, and then 4 dashes, and then you write the result. So that's very concise. You can just say query result, or query, and then anticipate that an error is thrown. Of course, we added our own tests. We added regression tests for defects. Whenever we had a defect, we added a test that the defect will never happen again. We added more finer-grained expectations. For example, you see here on the top right, we have this expect constant result. That's not in the usual SQLite tests. We added that to say, like, here we expect that HyPer can constant fold the whole query and just retrieve a constant result. So we were able to test way more than just the result. Well, but how to execute the tests? First, we had our own front end for running these tests. So there was the Hyper-D, our server, and then there was this test front end. But of course, this has a problem. You don't test the server protocol, right? Because you have this own content, this own front end. So what we did afterwards is we just wrote a client based on libpq because we speak the Postgres protocol. libpq is the client library for Postgres, and made that client parse the test file and send the queries to the server. That's great because now you can also test the server and the protocol stack, but it's way harder to debug because the server is no longer running in the same process, right? It's harder to debug. So in the end, I think we still have both. We have this front end that's baked into HyPer and the one that is a client, and both are valuable. Next slide. The cool thing is with these SQL level tests, we can just encourage you, use SQL level tests to do a lot of things because they are super concise and you can use them for a lot more than just testing SQL. For example, we use explain statements to test our optimizer. We send a query and it's an explain query. Here on the right side, you see we want to test whether deduplication works. We have a query that has 2 times the same subpart in it, right? This select A from T group by 1. And we want to make sure that the table T is scanned only once. So what do? We write an explain query and we just say, like, we anticipate that it shows what comes out of this explain. That's the query tree. That's the algebra tree. And we expect that this algebra tree looks like this. And you can see on the bottom line, we expect that there's only 1 table scan. If duplication wouldn't work, there would be 2 table scans. So this test would fail. You can test even more with SQL level tests. For example, what we did, we introduced a function to scan our own log file. So log, that's the process log. That's not the database log, the redo or undo log. That's just a log file that sends messages like, I opened a new connection and stuff like that. We added a function to just read the log So we could just write test cases that reason about whether something was written to the log. So that's pretty cool. If you pair that with trace settings that you can enable to print very specific details to the log. For example, you could print how many different join orders did the join order optimizer enumerate. And then you can test, okay, for this query, I anticipate that it enumerates 1,000 join orders or stuff like that. Or we want one step further, and we added special test functions that have side effects to test further internals. Of course, these are only in our debug builds. These are not in the released products. For example, a function that allocates thread local memory. So we can test thread local memory by just writing SQL, or a suicide function that just kills the process. And that, of course, is not in the final process, in the final product. You don't want to have it there. So you see, you can test really a lot with SQL, and that is very powerful. Next slide. In our team, and I think the controversy is still there, and there's no clear answer to it. So I showed you suicide, right? We tested killing the process with SQL. Should we do this, or should we rather have C++ or whatever language you're writing your database in unit tests? And there are pros and cons. Pros for SQL are, it's super easy to write, just one line or a few lines. It's super succinct. You don't need to recompile your database when you write a new test case. It's in vivo, so you can run code in your specific query context. You can test the whole query engine. You have very good test failure reporting, and you can update the expected test results automatically. And it resembles the customer usage of the system. So this is great. But then what is the disadvantage? The disadvantage is that you always test your whole SQL stack, right? You test your semantic analysis, you test your compiler, you test your storage layer with every query. So that's somehow cool, but sometimes you just want to say, I just want a unit test. I just want to test one thing. Then a C++ test might be better. And usually C++ tests, once they are compiled, they also run faster because they don't have to go through the whole SQL stack. But this topic is still a controversy, and it comes up with reviews over and over again. Someone writing a SQL test and someone saying, no, there should be a C++ unit test, or someone writing a C++ unit test and someone saying, no, this should be a SQL test, right? So just saying that it's interesting. Think about it. What is better to test with what? That's a big question. Next slide. Okay, but one thing when we were acquired by Tableau, we just had SQL level tests and C++ unit tests, but we quickly found out we need more. We need something beyond SQL, because what you can't test with SQL, you can't simulate load. You cannot open multiple connections. So what we did is we invented a load test domain-specific language, where you could just say, open a new connection. You could also embed the old test statements, right? Because we want to be able to compose that with our SQL tests. You want to be able to open 10 connections and run a test file in all these connections. We want to be able to execute things in parallel, because for load testing, it's very important to not have just one connection, but have hundreds. We want to have loops. So for example, you see here on the right, that's an example. You can execute statements, you can open a connection, you can repeat. Or here you see parallel 10. So you can open 10 threads, and each thread creates implicitly its own new connection and runs a query. And then afterwards we have and. So we say we spawn 10 threads to do the first thing, and we spawn 2 more in addition to do the next thing. So this helped us tremendously with load testing, because load testing and also load benchmarking is often overlooked also in academia. You just run your TPCH, each query one after another, and you say like, I'm super fast on this query. But usual database servers, right? They have hundreds of people working on the same time. So it might be that you're fast when you only work on one query, but if you have to work on hundreds concurrently, you slow down. So you need this testing. Next slide. What you also definitely need is A/B testing. We invented some tools, we call them MaxPerf and Query Runner for this. Because what you want to do is you want to check the compatibility with the old engine, right? You want to say like, okay, is this change correct, or does it yield a new result? And what we want to do, we want to do A/B testing on our 60K public workbooks that I mentioned before. And how it works, it's not so difficult. But but it helped us tremendously. What you do is just you write some code that starts HyPer, loads a workbook in Tableau, and that sends queries to HyPer, and then checks the number of marks in your Tableau visualization, checks whether the marks are at the same place for the A and the B commit, and then, yeah, you can test between old and new branches, right? So you do a change, you do an A/B test from the old to the new, and you hope that A, the results stay the same, and B, you get faster. Here on the right, for example, we have such an A/B comparison, and you see it shows these 60,000 workbooks, and you see most of these workbooks, every dot is a workbook. Most of them are at the 0% line, right? That means these workbooks stayed as fast as before, so nothing changed. But you see some are green, that means they got faster. So whatever this A/B comparison compares, it seems to be an improvement, right? Because some workbooks get tremendously faster. One workbook gets 800% faster. So this A/B testing is very important also to catch regressions. You never want to have dots above the 0% line. There's one, but it's an outlier here. You don't want to have a lot of dots that get slower, right? Next slide, please. And you want to automate that. You want to have automatic regression testing. This was also very huge for us. So this is automatic, what you see here. This is an automatic process that runs for every commit. And if you regress a workbook, it automatically files you a defect. It says like, hey, you got 300 milliseconds slower from this and that change list. And you see here in the picture, it also tries to make sure that it's not because of noise. So it runs the test multiple times and it has some leeway where you can get slower, right? Because you don't want to have a defect just because, well, your machine is noisy. So what you do is you just measure perf on every commit. If it regresses, you file a defect. And you make sure by running it multiple times and having leeway that it's not just noise. And now the fourth point on this slide is very important. If perf improves, you automatically update the expectations. You say like, okay, seems it improved. So now I say like, it has to stay that fast, right? So you have to update your expectations. That's very important. Finally, you also want to do more complex testing like fuzzing, right? So how does it work? You use a fuzzer, you feed it the SQL grammar, and then you let it fuzz for quite a long time. And we found several vulnerabilities and defects with fuzzing. I think the next talk in this session, it has at least something with fuzz in the name. So I guess it's about fuzzing. So definitely do this. You can find crashes. You can find memory corruption. It's awesome. Next slide. Finally, you also want to start before you test. You want to have static code analysis because it will help you tremendously with reducing the number of tests you need just because it makes your code quality higher. So just some things that everybody should do, not only for industrial systems, but also for your benchmarks. Even if you write a throwaway benchmark, do this. Because if you have a defect in your benchmark, it could invalidate your benchmark results, right? Enable all warnings and make them errors. So make it that your code doesn't compile if you have a warning. Keep your code clean. With C++, for example, you can use clang format, clang tidy, enforce that. Our continuous integration enforces clang format. You're not allowed to format your code incorrectly. Use the clang, that's of course only valid for C++, but for other languages, similar tools exist, right? For C++, if you're using clang, use all the clang static analyzers that you can. Address, thread, UB sanitizer, all of them. But beware, for example, for thread sanitizer, you must also build your third-party library with a thread sanitizer, otherwise you get problems. So it is a lot of work, but it still pays off. Do it. And also, of course, do things like test code coverage for your test cases. And so get all the tools that modern software engineering gives you for improving your code quality. Next slide. And one final thing that haunted us, I think that haunts every product in software and where you have to be very careful, be sure that you don't have flaky tests. They are the root of all test evil. A flaky test is a test that sometimes passes and sometimes fails. And in the worst case, it almost always succeeds. And just once every 40 days or so, 2 times a year, it fails. don't let these flaky tests build up. So if you have a test, you run your test all over again, and sometimes it's red. That's all your alarm bells have to ring. You have to make sure that you hunt this down. Don't let these tests build up, and don't get into the habit of muting them, right? Because you could say like, oh, it's sometimes red, it's sometimes green, I don't like it, I mute it or I delete it. Don't do that. Treat them as high priority defects, also in your academic projects, because they could show you a very deeply underlying bug, and they kill your productivity. Because if you're just looking for things to be green and they are sometimes red, you get randomized, you don't like this. The root cause could be a real defect, but it could also be a bad test. That's usually timing dependent, where you have a test, do something, wait 1 second, and then make sure something happens, right? And sometimes your machine is slow, your machine has a bad day, so this 1 second is not enough, so the test fails. So make sure you kill flaky tests at all possibilities. Next slide, please. Okay, so now we go to the lessons learned. What did we learn from porting HyPer or in general? When you do benchmarks in academia, benchmark responsibly. So when you benchmark a system, right, especially when you benchmark a commercial system, contact the vendor. So if you want to benchmark HyPer, talk to us, right? Report bugs. If you find that HyPer crashes, be nice to us and report us a bug. Say, hey, HyPer crashes, thank you. Share your benchmark ahead of time if possible, because this allows us to give you feedback and double check the validity of your benchmark. And therefore, it gives you a good chance to increase the quality of your benchmark. Here, I wanna say, like, shout out to Andrew C. from Brown University, who did just that. He's working on something, and he did a benchmark, and he included HyPer, and he just wrote us an email. And it was great for both sides, because he, with his benchmark, he uncovered a defect in HyPer. So thank you. But we also, by looking at his benchmark, we also uncovered a defect in his benchmark that would have, for some queries, given him invalid results. So this can really help both sides. And finally, also ask the vendor, ask the vendor how to configure the system, right? Because if you just misconfigure your contenders, this impacts the credibility of your hard work, right? It's like, oh, you're 10 times faster, but just because you totally misconfigured your contenders, that's not cool. Think about how to configure your contenders correctly, then your results get meaningful. Next slide. What we also want to say, like we also did this with our 2018 paper, there's more than TPCX, TPCH, TPCCs, TPCDS, right? They are great benchmarks, but generated workloads are real. It's not just Tableau. More and more BI tools, enterprise resource planning tools, they all generate queries. And these queries are way more complex than handwritten TPCH, TPCDS queries, right? TPCDS is already a bit more complex, but it's still far away from what generated queries are. And therefore, also a lot of interesting and novel problems are lurking in these workloads. So it's also that by just checking out these workloads, you could have a lot of interesting ideas for papers that you would no longer get out of TPCH, because everybody has already optimized TPCH to death, right? So here, another shout out. If you want to play with a more real world benchmark, consider the public BI benchmark from the CWI. They released them in the white box compression paper in the CIDR. And it's based on Tableau public data. So it's based on our data, but these guys from the CWA, Peter Bonds and his students were so nice to scrape the data from Tableau public. And as I said, that's allowed because it's a public data set, and they uploaded it to GitHub. So play around with that, and you could get a lot of interesting insights into your project by just not running it only on TPCH. Next slide. Also, one thing that we can only say to you, right, because we did it and it was great, build your system for production. Build your research systems as if they would one day become a productive system. First, it's better than building a throwaway prototype, because I mean, we did it. We can say it firsthand, right? It's way more rewarding. It's a longer lasting sense of achievement. It's way nicer to have something where you build upon it and it's a nice code, it has great quality, instead of just having a throwaway prototype that somehow works, that just segfaults if you input the wrong values, and then you throw away after a few months. It's also easier to build upon that, right? If your next paper needs something again, if you have a stable system, you can work again with that. And you get results that are way closer to reality. Because if you just build micro benchmarks, they often leave out crucial parts. They leave out logging, they leave out recovery, and so on. So it could be that your results are nice, but they would never be the same in a real system, because real systems have to do logging and such, right? Also, next thing, follow standards. Follow the SQL standard, follow Postgres, or follow a common open source standard, because it will help you a lot with benchmarking, with test adaptation. You can just use the SQLite tests, you can share tests. Don't reinvent the wheel, use standards. And finally, build your system as if it was for production. Build it with great quality, maybe test-driven development. It's also great for academia, right? I mean, we were also in academia. Usually you say like, why should I go even have test cases for my, it's just a prototype. But if you have a defect in your prototype, your results could be absolutely invalid. And that would be very bad for your paper. So think about also having high quality for the things you build for academia. It allows you also to adapt the system to the next benchmark. If it's stable and doesn't segfault with a different result, you can just use it for your next benchmark without having to hunt down these crashes first. And finally, we can say that because we did it right, there is a real chance to get your system into production in the end. So do it as well, you can do it. And finally, also think about OS compatibility. We've seen in a lot of papers some perfects where it's like, yeah, we patched the Linux kernel to do that. Yeah, that's great, but that means you will never be able to publish that for Windows, right? So if you want to ever get a system that also runs on Windows, don't do these perfects. Okay, it's cool for some papers, but yeah, it would also be nice to have something that will also run on a different OS, or will also run on ARM, for example, on a different on a different CPU, right? So this helps you tremendously here. Next slide. Okay, that's the conclusion. Back to you, Toby.
Thank you, Jan. So we are wrapping up. First is academic projects can make it into production. It's a lot of fun, and we encourage you to do the same. Follow our path. It is really a fun story, and as Jan said, it's a long-lasting achievement, right? Replacing an old system, which is usually the case, right? If you come in as a newcomer, is good, right? Because you have a point of comparison, but it's also really hard in the corner cases, right? Again, the long tail is haunting you. The second thing we want to stress is TPCX benchmarking is not everything. We had to learn the hard way at Tableau, 27 megabyte of SQL, very, very complex calculations. A lot of applications today, they generate queries. It's no longer humans writing queries. There's various layers of testing required. Don't forget stress testing. Don't forget regression testing. Don't forget automation. Think about flaky tests. This is really, really important if you want your project to have a long-lasting effect. And finally, benchmark responsibly. The vendors, they will have an ear for you. They will get back to you. You can try out HyPer through the HyPer API. We put the link on the slide. If you want to try it, if you find something, please let us know. And with that, thank you very much for your attention. If you have questions, I think we have very little time. We're very sorry about that, but you can also reach out to us directly. Thanks.